I don't know if that entrance was dramatic or weird, but it was one of those. Find example 7 in your notes packet, if you can, if you have it. If not, I wrote most of the text up here, and we'll write the rest up as it becomes necessary. It says we've got this satellite, it's orbiting a planet. Let me draw a picture based on the text while you go ahead and read that. So that's what it says. We got what's going on, right? We've got a planet, there's its mass, there's its radius, and then here's the satellite orbiting out here. The reason I picked kind of somewhat contrived things for like the height that it is above it is so that it works out a little bit nicer. I'm not going to do something like, all right, here's satellite, it's orbiting at a height of 150 kilometers above the surface of the Earth, because then the numbers that you have to work with are obnoxious, and there's a lot of calculator work involved. So this is supposed to get you able to do that same kind of question, but without the obnoxious calculator work. All right, the first question about determining the gravitational potential energy of the satellite while in orbit is extra super straightforward. If it just says like calculate the gravitational potential energy, that's just use the formula. Of course, we have to use our new formula of negative GMM over R. And then really the only extra thing we've got to plug in here is exactly what is R, right? R is, we can't just leave it as R. R is where is the satellite relative to the center of the Earth. Well, that would be not 2R, but rather to the center of the Earth, so a grand total of 3R. All right, and that's its gravitational potential energy up where it is in orbit. All right, part B now. It wants us to find the total energy. What other kind of energy would a satellite have while it's in orbit? Okay, clearly there's something missing from my picture. If you think back to the article that you read, it's not, you don't just get something up really high and then it just like sticks there in the sky. The way that you get it up there in the sky is you have it move really fast, sideways, right? So it's got to have a certain amount of energy to get up that high, but you also have to give it a lot of kinetic energy in order to have it be able to move at orbital speed. So in other words, it's got not just its gravitational potential energy, but it's also got kinetic energy. So what I'm going to do with this, rather than, clearly I'm at school, rather than crunch a bunch of numbers and that kind of thing, what we're going to do here is, number one, derive a generic formula that you can actually use for the total mechanical energy of any circular orbit. Now, anytime you use this formula, you're going to derive it, but honestly, it's always going to go the exact same way. Okay? So here's how it begins. If I want to know the kinetic energy of something in a circular orbit, I would have to know what its orbital speed is. All right, well, we've done that before. We've calculated orbital speed. We do that by saying, well, it's moving in a circle, so centripetal force. And the force that makes it move in a circle is the force of gravity. So that means the centripetal force equals the gravitational force. Okay, plug in the formulas for those things. mv squared over r equals gmm over r squared. A thing that I hadn't brought up before, but I'm going to remind you of it now. Force and field for gravity both have an r squared in the denominator. Very frequently, people will goof and say not square that one when they're supposed to be calculating the force. The opposite is true for gravitational potential energy. Please notice it's not squared, just regular r. Okay, so don't make that particular goof. All right, that aside being done, let's finish up what we were doing. we were finding the formula for the speed so that we could find the kinetic energy. So the m and one of the r's cancels, and we get v equals root g big M over r. All right, so that means the speed depends on the orbital radius, right? The larger the radius, the slower it can go. Because it's farther away, it's a bigger circle, it's easier to go in that kind of a path if it's a bigger circle. All right, so that means that if I plug in for kinetic energy, which is 1/2 mv squared, I'll get 1/2 little m. This squared is just going to remove the radical, so gm over r. So if you like, then that means the kinetic energy is gm over the 2 and the r are both in the denominator, so over 2r. Okay, and then the potential energy was negative gmm over r. That's good. All right. Well, those look pretty similar. I think I'm going to go ahead and combine those like terms and see what we get. Or they're not quite like terms, but if you think about this one here as being more like 1/2 gmm over r, which is what it is, right? Gmm over 2r is half of gmm over r. Now we've got like terms where it's like 1/2 minus 1. 1/2 minus 1 would be negative 1/2. So that means that our total mechanical energy, I should have used that term, so reminder here. All right. The total mechanical energy is going to be kinetic plus potential, and it works out to, for any circular orbit, gmm over 2r. For any circular orbit that you want to talk about, that's what it's going to be. Okay, so if we're orbiting at some other radius than what it is, I could just plug in the new orbit for that circular, new radius for that circular orbit, and I would have the new mechanical energy. For our particular orbit here, we already established the orbital radius is 3r, so I'll plug in 3 times the radius of the planet here, and we will get negative gmm over 6 big R. All right, there's the answer. All right, I'll pause the video while we get part C and D going. So anytime we talk about orbital mechanics, meaning like the science of putting things into orbit or how they are in orbit or can move from one orbit to another, they're always talking about changes in energy. So there's a certain amount of mechanical energy for a given orbit. That formula that we came up with before, remember, was the total mechanical energy was, moments ago, negative gmm over 2r. Right? And that was the total mechanical energy of any particular circular orbit you want to look at. Just plug in a new value for r, and you've got the new mechanical energy. Like with the formula for gravitational potential energy in general, mechanical energy has a maximum value of 0. Right? That's the most it could be. And then, as we'll learn later, technically, if the mechanical energy of an orbit is 0, it means it's not in orbit. It means it's actually escaped, meaning it's going away from the planet and never coming back. Okay? So if it's negative anything, then it's in some kind of an orbit. Okay, well, the energy that it had in orbit was, from part B, negative gmm over 6r. That was the mechanical energy of the orbit. Of course, the satellite started on the surface of the planet and was presumably, roughly speaking, stationary. So that means that you had to add a certain amount of energy to the satellite to move it from here to there, and also with the required amount of kinetic energy. In other words, the rocket engines that you attach to the satellite did enough work to move it from being at rest at the surface to at orbital velocity this high up above the planet. Okay, so let's go ahead and work through what you would do here. Really, you're doing kind of like a work thing. You're saying the work done by the engine, the rocket engines, equals the change in the mechanical energy of the rocket ship. Okay, all right. It's going to be E final minus E initial. All right. If you've just got something like a meteor falling to Earth or something like that, then you wouldn't have any work in there. It would just be E final would equal E initial, and both of them would be some amount of kinetic and potential plus some amount of kinetic and potential energy. In this case, though, there's rocket engines doing work. Okay. The final energy, we already worked out what that was. The sum of the kinetic and potential energy is negative GMM over 6R. Okay. For the initial energy, in general, you're going to be able to say, like, all right, some amount of kinetic, some amount of potential. All right. Assuming that the satellite starts at rest on the surface of the planet, the initial kinetic energy is 0. Don't care about that. My phone says I should be taking attendance on you guys. Are you all here? Are you all here? Oh, good. Okay. For the initial energy, that's going to be, go back to our formula for it, negative GMM over R, and the initial energy is going to be at the initial radius, which is at the surface, which is the radius of the planet. So that's going to give us this. Okay. So minus a negative is plus a positive. So basically it's going to end up being GMM over R minus 1/6 GMM over R, which is going to be 5 GMM over 6R. Okay. So again, if you're like, what does that mean? Well, plug in values for things if you like. If you wanted to say, all right, this is orbiting Earth, plug in the mass of the Earth and the radius of the Earth, and this tells you how much energy, like how much rocket fuel you need in order to move something from the surface of the Earth up to this particular orbit here. That's what that result is telling you. All right, let's look at part D now. This last part is actually probably going to be the most common kind of thing that you'd have to answer in the next homework. Take careful notes on this and bear that in mind when you're looking at your homework. A lot of what you're going to see is going to be sort of like this. So the idea here is if you just drop something from a really high height, that's essentially what's going on here. So if it's instantly brought to rest, just stops here and then falls towards the Earth, how fast is it going to be moving when it strikes the Earth? All right, let me pause video and write some algebra up here. All right, the idea here is it's a conservative system. It's being dragged towards the Earth by the force of gravity. So the initial and final energies are going to be equal. In both, you're going to say you've got K plus U. All right, that's going to be the general setup for how most of these are going to go. The initial kinetic energy is going to be 0, because remember we're saying it was brought to rest by its collision. Bam, stop suddenly, okay? There's our initial gravitational potential energy, okay, because that's how high it is. The number one blunder here is usually people forget that the final gravitational potential energy is not 0, but is this right here. All right, and then we're supposed to solve for this V. Let me pause again. The rest from there is algebra, so pause, ponder the algebra as you see fit, and there's the answer. That helps.